Hi, I am Yoon. Paul, Jack, and I are going to talk about rigid body's acceleration. First, I'm going to go over basic concepts of general plane motion of rigid body's acceleration and explain how the acceleration of 2 points in the rigid body is related through formula. If there is a single bar, if it moves, the 2 points A and B of the bar will move at the same velocity and acceleration. However, if an additional movement is added to rotate one point, in this case point A, to the axis, the other point B, based on one point A, will be given additional acceleration, which are tangential and normal acceleration. The acceleration of B with respect to A is represented like the sum of tangential acceleration and normal acceleration. So the equation will be the sum of acceleration A and acceleration of B with respect to A, and the acceleration of B with respect to A is the sum of tangential acceleration and normal acceleration of B with respect to A. How can you represent the tangential acceleration and normal acceleration? The tangential acceleration is dv dt, and v is equal to omega times r, and let's differentiate omega times r with respect to t. The omega dt r plus omega dr dt. dr dt is 0 due to r is always the same value. As a result, the tangential components represent like alpha times r, because the omega dt is r. Let's see normal components of the acceleration. The normal components is equal to v squared over rho, and v is equal to omega times r, and rho is r. So it's a simple math. The normal components of acceleration is omega squared times r. So acceleration of B is equal to this translation term, and these two terms which are represent the rotation motion of the rigid body. As a result, this term represents the translation of the rigid body, and these two terms which are related to the rotating motion represent rotation of the rigid body. Paul and Jack are going to keep talking about acceleration of the rigid body through some example problems. Thank you.
Hello everyone, here's a problem with the rotating disc in this direction, and link AB moves that direction together with the disc. The question is, what is the acceleration of point A and point B, and what's the angular acceleration of this link AB? And with the given and find information, we move on for the solution at point C. That is acceleration of the disk times this distance. We substitute and we give 0.6 meters per second squared in horizontal I direction. And so to continue on, we apply this relative acceleration equation at point A, which is acceleration of point C plus angular acceleration of the whole disk cross product with the position vector of CA minus angular velocity squared of the disk times this distance AC. We substitute everything in it and we receive angular acceleration of point A in I and J direction, positive and negative. Positive I, negative J will give this vector A. And magnitude of this vector is square root of components in X and Y direction, or I and J. We substitute it and we receive this 1.34 meters per second square acceleration of point A right here. And we move on direction of point A. If we need to find out what's the angle, we take inverse tangent of J over I component and we receive 26.6 degrees, which is right here, this angle between horizontal line and the vector. Now we move on and find position vector of at point B right here, that is OB minus OA, and we receive this 0.4 in I direction and negative 0.3 in J direction in meters. And we apply relative acceleration equation at point B, that is acceleration of point A plus angular acceleration of link AB cross product with that position vector AB we just found, and minus angular speed, angular velocity of link AB times the distance AB, and that is 0 because, and this is link AB, this is velocity vectors at point B and at point A. They are parallel to each other, and so perpendicular to them lines are parallel to each other as well, which means that the center of rotation at this instant is at infinity, and that means that angular velocity of this link AB is 0. That's why this becomes 0 and we work with whatever is left over. And as we go through, we equate I and J components together and receive these values right here. And so to move on, we get these equations from I and J components. Equation 1, AB equals this, and from J components, we get this equation. Through this equation, we find angular acceleration of link AB, which is 0.6 meters per second squared over 0.4 meters, and we receive angular acceleration of link AB is 1.5 radians per second squared. And we substitute this into equation 1, and we get this acceleration of point B, 1.65 meters per second squared. And this is the final free body diagram of the link AB, with shown velocity and acceleration vectors, and angular velocity and angular acceleration of link AB.
This is example problem in chapter 16, problem 116. Says the disk has an angular acceleration of 8 radians per second squared and an angular velocity of 3 radians per second at the instant shown. If it does not slip at point A, which is right there, determine the acceleration of point B. So I've transferred that over to here. So we got our given is that angular velocity is 3 radians per second and the angular acceleration is 8 radians per second squared. and we need to find the acceleration at point B. So I went ahead and drew the free body diagram here, where we have a radius of 0.5 meters and an angle between point A and point B of 45 degrees. And there's the origin labeled O there, and we can see that it's moving to the left at that velocity and acceleration. So to start off, at both the angular velocity and the angular acceleration are both in the positive k hat direction. So we know that right from the start. Then the first part to solve this problem is we got to find the position of point B relative to the origin or the center of the disk. So for that, we have equation of the r vector as B is from the origin. We have 0.5 meters, which is the radius seen there. And then we do the sine of the angle between point A and point B, which is 45 degrees, and that is in the I hat direction. So sine is, it's opposite over hypotenuse. So opposite of the angle we have right here is this dashed line, and so that is in the x direction or the I direction, going to the right. And then we have minus 0.5 meters times cosine of 45 degrees in the j hat direction. And so that is in the y direction. Cosine is adjacent, which is this line here, over hypotenuse. So that is how far the point B is away from the origin this way, which is in the y direction or the j direction. It's negative because we have the origin here and it goes down, which is right there. So when we solve for that, we get 0.35 times I hat minus j hat meters. And that is how far B is away from the origin, as you can see right here. Next, I want to find the acceleration of point O, or the origin of the disk. And to do that, we know that the acceleration of the origin, which is going to be going this way to the left or in the negative x direction. So we have negative 8 radians per second squared, which we get that from the problem statement, and that is times 0.5 meters in the I direction. Then once we solve for that, we get negative 4 meters per second squared in the negative I direction because the disk is moving this way and the positive I direction is this way. Flip this over here. Finally, we want to find the acceleration of point B relative to the origin. And this is given by the acceleration equation. The acceleration of point B is equal to the acceleration of the origin plus the angular acceleration times the relative position of B to the origin minus the angular velocity times the relative position of B to the origin. Plugging in numbers, we get negative 4 I hat plus 8 k hat times 0.35 times I hat minus j hat minus 3 radians per second squared times 0.35 times I hat minus j hat. Now we solve for that and we end up getting negative 4.35 in the I direction plus 5.95 in the j direction. Then we take the square root of the sum of the squares and we get 7.35 meters per second squared for the acceleration of B.